As we begin Chapter 5, Experimental Design, we need to ask ourselves the question, what's the difference between a confounding variable and a lurking variable? And it's a difficult question to answer because there are so many similarities between the two types of variables. So let's talk about those similarities first, and then I'll go into a discussion about how they're different. So confounding variables and lurking variables are both similar in the sense that they are what we call extraneous variables. Extraneous variables, as we can imagine from the root of the word ext, think exterior, something that happens on the outside looking in that affects the outcome of an experiment. I used to have a baseball coach who always used to say you need to block out the extraneous variables. And we'd always ask him, what does that mean? And his response was things that you really can't control but still have an impact on the game. So obviously a player's performance has a direct impact on the outcome of the game, but there are other factors that do play a role, such as weather, such as the ability of the other team, and sometimes if you're a visiting team, the environment of playing in another team's stadium can have an effect on the outcome of the game. Now, these are all extraneous variables because we can't control them. So it's a very similar analogy to what you would do in any basic experiment. There's confounding variables, there's lurking variables that you can't control, but they still affect the outcome of the experiment. So what's the difference between confounding and lurking? Now, I have two working definitions here, and they're both very similar in nature. The biggest difference is confounding variables are easier to measure, and they're also included in the study. So what I mean by that is they're easier to detect, and oftentimes the researcher or the statistician or the experiment, whoever's conducting it, will take into account those confounding variables. Whereas a lurking variable, think of that word lurk, right? If someone's lurking, they're kind of hanging out, not really on the surface, beneath the surface, but they still have an impact on the situation. They're often difficult to measure. And the biggest difference that I like to explain as distinguishing is a lurking variable will affect both your explanatory variable and the response variable. And that, I think, makes a little more sense by looking at a diagram. So let's start with confounding first, and then I'll compare our diagram for confounding to a diagram for lurking variable. Okay, so there's three parts to the process here. Let's say we have our explanatory variable over here, our response variable over here, and you know what, let me just label these real quick. Let's say here is our explanatory, and this box over here will be our response, and then this box down here, let me go beneath it, we'll say that is our confounding variable. Okay, so this box down here is confounding, this is explanatory, and this is response. Now, let's think of a scenario where we could have all three of these parts play a role in an experiment. So let's say we wanted to see the effects of a certain fertilizer on the growth of a plant. More specifically, let's say the growth of a tomato plant. And in your experiment, you decide to plant 10 of these tomato plants in an area that is underneath a tree. So it's not getting a lot of sun exposure because of the tree. It's blocking out a lot of the sun and it's underneath the shade. So let's say 10 you plant underneath the tree, and then 10 you plant out in the open. So it receives direct sunlight. Those 10 plants are then also given a fertilizer. And then after 2 months of growth, you compare the two results. Now, one would imagine that the 10 who are receiving the fertilizer are going to experience a bigger rate of growth, and they're going to be bigger tomatoes. The confounding variable here would be that they're also exposed to the sunlight. Obviously, plants that are exposed to more sunlight are going to grow at a faster rate. So on the surface, once again, what we're studying as a person experimenting this would be the administering of fertilizer. So let's just say our explanatory variable is fertilizer, and our response would be the size of the tomatoes. Obviously, there's a direct influence on fertilizer and the size of the tomato. But the confounding variable here would be exposure to sunlight. Okay, notice how that's an extraneous variable. We can't control it, right? The sunlight's obviously independent of what's going to happen in those 2 months, but it plays a role in the size of the tomato. And that's how we have this arrow here, this arrow obviously here. Here's the direct relationship. Here's the confounding relationship. The exposure to sunlight has no influence on the fertilizer. And that's always where I start to explain the difference between a lurking variable and a confounding variable. You'll see a link between this variable down here and explanatory for a lurking variable, but not for confounding. So let's do this. If it's still not making sense to you, I'm just going to copy and paste this down here. And we're going to do a different example in the bottom to show you how that works. So let's just take this out. We're not going to use fertilizer, tomatoes, or tomatoes. We're going to take all this out. And now we're going to look at what a lurking variable might be. Very similar to confounding, but different in the sense that it's going to affect both your explanatory and your response. So let's get a little more serious. Let's say we wanted to look at the amount of firefighters attending a fire scene and the amount of damage that is done to that building or that fire scene. So there's a direct relationship between, I'm just going to say our explanatory variable is the number of firefighters deployed for a 911 call. And our response variable would be the amount of damage done as a result of a fire. Okay, let's say we were conducting an experiment that wanted to see the difference between these two. Obviously, we know there's a direct relationship between the number of firefighters and the amount of damage done, right? The more firefighters we have, the less damage is going to be done, right? It's called an inverse relationship. When one increases and the other decreases, in this case, the number of firefighters are increasing, the amount of damage is decreasing. So there's definitely a direct relationship here between these two. Now the lurking variable, in this case, would be the size of the fire. Right? Not once did we mention how big the fire is. All we're doing is measuring the amount of damage done from the fire. Okay, well obviously we have 20 firefighters in the scene. That's going to help alleviate some of the damage. But the size of the fire is a really huge factor in determining how much damage would actually be done. Now notice the difference between confounding and lurking here. We have to ask ourselves this question. Does the size of the fire have an influence on the number of firefighters deployed for a 911 call? And the answer is yes. Right? If we receive a call, we're dispatched for our firefighters, and we get an idea, is this a large fire? Is it a small fire? That's going to directly influence how many firefighters we call to this building. So here's what I'm going to do. With this diagram, I'm actually going to move this thing down a little bit. And we're going to keep this arrow in. All right, there's still obviously a relationship here. And let me just get that lurking variable down here. But now what I'm going to do is I'm going to copy and paste this arrow. And I'm just going to add one more part to this diagram. See how it's kind of a three-way relationship here now? You've got this lurking variable affecting both your explanatory and your response. Whereas for confounding, it's just affecting the response variable. So that is the difference between a lurking variable and a confounding variable. I hope this video makes sense. If you're still confused, just shoot me an email. Thank you.